this one, Ken.
Okay.
Unlike the Chief, I parked in a very safe space, next to the poles and close rooms. If it picks up any injuries, I'm probably in trouble. George, this is the timer. Is it?
Yeah.
This time?
Yeah.
Okay. Well, let's go ahead and get started today. There's always an opportunity to ask questions, before we start, after, during, whatever. If there's any questions, by all means, give a holler. I think I told you where I am too, over in 147, over in food science. Got any questions about this or whatever? Certainly stop in. Happy to have you. So, but our topic is flavor. It's a flavor food. It's being covered very, very broadly. So we're covering many aspects of it. We do offer this as a full course for a full semester. Then, of course, we get to go through it in much more detail. So we kind of give it a skim. How's that at this point? So we talked about a little bit about the industry. We've been talking about how flavors are formed in plants particularly. And that's kind of where we are at this point. I guess we talked about olfaction, didn't we, and sensory perception. So we got that one in too. So now we're just dealing with how plants taste differently or why they taste different. Because we certainly appreciate that we do. That's especially true, as I mentioned, about fruit. We really recognize different oranges, different types of apples taste different. We don't necessarily think about it for carrots or beets or whatever, but it's exactly the same for vegetables. It really depends upon many factors, and this is kind of where we were here, and mentioned about soil, how important soil is, and nutrition of the soil. That's basically where any sulfur comes from. Nitrogen can come from the air, it can come from the soil. And these are two compounds, two elements, two atoms that are very important to flavor, sulfur and nitrogen. Plain old carbon isn't very interesting. You put a little nitrogen in there, put a little sulfur in a molecule, and it really becomes interesting to us. So, as I said, soil then certainly makes a difference. The nutrition of the soil, mentioned about radishes. Rainfall, also mentioned something about this. When you get abundant rainfall, you'll tend to get larger fruit, larger vegetables, but they'll also tend to be less flavor. It's fascinating to me that, you go in the grocery store and you pick up a lemon. And so the lemon may be some little wimpy lemon such as this, but it has the same amount of flavor as a large, not a really big lemon, but a bigger lemon. There's a certain number of oil sacs on that peel, on that surface, and that's the same number on a big lemon as a small number. And that's where your lemon oil, your major lemon flavoring comes from. So don't be fooled by buying the biggest one and think you got the best deal out of the whole thing. Sometimes the scrubs, the wimpy, the ones that have had a rough life, end up having a better flavor than those that have had an easy life. This, and that gets into ease of life here in terms of temperature. Generally, the larger the temperature extremes, the swings, it puts stress on the plant, and the plant responds by putting out certain metabolites, building certain metabolites, increasing them that can increase flavor. So it's really interesting. Maybe I mentioned, I forget, but California used to be really a lemon capital of the world. Italy, #1. California was #2. And where were the lemon trees? They were along the coast. So you get the cool breezes coming through, the rains, the time temperature. It was absolutely beautiful for those lemon trees, happy as can be. Then people moved in, of course, and there were the lemon trees, and they moved into the deserts. So now they're being irrigated, and they're irrigated more into Arizona in that area. And now we're kind of at the bottom of the rank in terms of quality of lemon oil. Just where you grow things, what the environment is extremely important to us. And this one, of course, the idea of maturity. And so pick a fruit early, allow it to ripen away from the plant. It's okay in the case of avocado and cantaloupe. They really are perfectly fine. Some actually have to ripen off the plant. But there's not many of them, by far. Most of them really benefit from being vine ripened. Our tomatoes have been a joke from a flavor standpoint, a sad joke, in that we've gotten away from locally grown so far that we find tomatoes are picked green, they're not mature, they're not in a position where they ripen to the same flavor. And for many years, I think we could have replaced our tomatoes with, nice little plastic neon red piece and probably been better off in terms of quality. Just wash the darn thing and use it again because there's such poor flavor to the tomatoes. So growing them locally certainly does help them, or help us, I should say. And this is where I think I mentioned something about peaches. Peaches get their flavor from a group of chemicals called lactones. If you artificially ripen them, pick them green, allow them to ripen, they look beautiful, they only have 20% of the flavor, 20% of the compounds that give those peaches flavor. 80% is gone. And what scares the heck out of me is that some people will never know that. This will be the new standard. This is what people will think peaches are until they go to some place where peaches are grown. They pick one off the tree and say, oh my God, that's beautiful. What is that? It's a beautiful peach. So we really have a problem with our system. In many parts of the world, guess what? When things are ripe, when they're available, you eat them. When they're not ripe and locally grown, you don't eat them. And that's just the way it is. Our system has said, well, let's make these things available all year round. It doesn't make them better. It tends to make them much, much poorer. So this is probably one I didn't get to, and that's talking a little bit about bananas and the idea of post-harvest storage. I said it takes 60 days for green beans to get up here from Chile. 60 days. Well, what happens? How did they look after them? If you look at apples, we'll have apples all year round. They'll pick them, harvest them, and store them. And oftentimes they're stored under reduced temperatures, or that they're in a special atmosphere, which I'll mention in the next slide. But temperature of storage is extremely important. And this is probably one you're all aware of, I would think, or at least part of this aware of. You don't put the bananas in the refrigerator. Why don't you put the bananas in the refrigerator? Because at lower temperatures, it inhibits really the flavor of flavor development. You notice the peels turn brown. The interior is perfectly fine. It doesn't hurt them. They turn brown on the outside. I don't eat the peel anyway, so it's kind of irrelevant. If you let that banana ripen to the point where it has full flavor, you can put it in the refrigerator. You put it in the refrigerator when it's green, not fully ripened, it will not develop the flavor. And we find really if we get cooler temperatures, even 10 to 12 degrees centigrade, 60% reduction in flavor. It's kind of the sweet spot in between. If we go storage over 27 degrees centigrade, they pick up a real high level of ethanol and ethyl acetate. Ethyl acetate, if anybody's familiar with nail polish remover, that is the chemical. The bananas will pick up that odor. They will develop, I should say, that particular odor. And so there's just a sweet spot for storage of bananas where they have the full flavor. It's harmed by cold, it's harmed by warmth. Now, of course, that's related to where the bananas are grown. The banana tree has never had to adapt to coldness or winter or harsh temperatures. And so they've been perfectly fine. Here's optimum, we're happy here. But if we don't store them right, we've got problems with the bananas' temperature storage. As I mentioned, the slide coming up, we want to slow down metabolism. We want to make that apple or that stored product have a longer life. We slow down its metabolism. And for this, typically reduce the oxygen somewhat, go from 20% down to 2%, so reduce it, by 90%, and add a little bit of CO2. That slows down the metabolism of the fruit. You got to remember, these things, they are living tissues. We may have picked them off the vine, but they're still, real machines going on. And if we let them simply go on without any slowing, they obviously will become overripe, the texture will be bad, the flavor will change. So what do? We try to slow things down. We slow that metabolism, and it's done by reducing oxygen typically and adding carbon dioxide. And so it's interesting. We get color and preservation, but we lack the characteristic flavor. Again, these things just don't develop the same flavor if they've been undergone this type of storage. It does a permanent damage to it. So temperature, humidity, and air or not air. Humidity is another one. This plant is respiration's going on. It's either giving up moisture, taking on moisture. You need the right humidity for storage, lighting. It's interesting, basically, what happens along these lines. You need all of these conditions to give that product the best flavor possible. If you don't give it lighting, you don't control humidity, you put in CO2 to inhibit it, it's not going to be the same product. I'm rather fascinated by the one down here, where I just kind of put this bit in. We're finding there's research being done on climate change and flavor. You're certainly aware of climate change, the effect it has on moisture, rainfall, temperatures, growing temperatures for crops. And we also have to be aware that it changes metabolism in a manner that affects flavor as well. So that basil, that spice, that herb, that food that once tasted in a certain way, it's going to be subtly different just because of the climate change that's occurring. People are starting to look at it. And this is an interesting one where there are companies in town that work on locally grown. Let's grow these in hydroponics. Let's grow these in greenhouses over winters. And this is one that a project on basil, where if you, a nice fresh basil, if you could grow it locally, there'd be an advantage to it. The finest basil comes from Italy, wouldn't you know? And so they've been working on it, but you don't get the same flavor. Now this is due to the spectrum, the light spectrum, that isn't the same here in greenhouses as it is in nature. And that's changing too. The light spectrum as it comes through our atmosphere due to climate change is changing the flavor of such things. So we live in a dynamic world, we really do. Idea, well, I guess this is a slide I should have gone to, is that our flavor is changing. And again, the CO2 down here in the atmosphere is certainly an important one in terms of that particular change. So, as I said, you accept, I'm sure, the idea of bananas and, well, not bananas, maybe it's not the best example. There's only one variety of banana that's grown across the globe that with any quantity. How's that? Commercial quantity, and that's a Cavendish banana. The previous variety of bananas that was grown was attacked by a pest and basically wiped it out, and so they're looking for other, what will grow, has this pest resistance. And people don't like seeds. So, okay, the Cavendish was the one that people tend to like. And now Cavendish is grown all over the world, and that's almost the only banana that's grown, until another pest comes along and takes care of that for us. But we recognize, okay, different plants grow in different places, taste differently. Do we necessarily walk out to the meat counter and we take a look at that piece of steak and say, what's that going to taste like? I wonder how that animal was reared. I wonder what its flavor is going to be. You know, we don't tend to think of that. Maybe grass-fed has gotten us into that. If you are into grass-fed beef and you taste that with a normal beef, or any animal, grass-fed versus a more what's now commercial process of fattening on corn, and in the last days a richer diet, a higher fat diet, you'll find that animals also taste different. And I don't know if I notice as much difference between a black cow, brown cow, or whatever, red cow, but certainly the diet makes a real difference too in that animal and in the flavor of that animal's products once it's cooked. And so that really goes into the whole idea that fats, there's different fats, different lipid compositions in different feeds. We tend to deposit some of these fats in our body or the animal's body, and that fat, when being cooked, you cook the meat, there's fat there, it develops a certain flavor depending upon what type of fat's present. So it's interesting, animals will taste different. So depends upon feed, primarily what that animal's eating. We also have a habit in the U.S. of aging our red meats. And so that's certainly beef, lamb, if you're a hunter and you'd be out for deer, whatever, there's always an aging period that goes into the product. And what are we doing during the aging process? We're basically letting enzymes in that animal. The animal's dead, but believe me, there's still enzymes there that will go ahead and break down some of the proteins. They'll make changes in those tissues. They'll produce precursors of flavor that develop when heating. So diet's one effect, but also a cultural habit. Some cultures, they kill an animal and they eat it. There's no aging goes on. We tend to age it. And the comment here that many people who are in the meat industry and familiar with this, what they do is they age it until it's about to walk off by itself, hanging on the hook because it's been aged so well, or not. So the idea of the more aging, the more flavor it has, and what's that break point between that's really over the hill, or this is better. But it's interesting. So, you don't expect animals to taste the same, meats to taste the same. You don't expect fruits or vegetables to be all the same. So it's a fascinating area. And like I say, it's going to be gaining more attention as we go see climate change occurring. Things will be changing on a global basis. Well, that's what nature provides for us through plant tissues. We also then, of course, develop some flavors of our own on our own effort. Let's put it that way. It's a better terminology. Non-enzymatic browning is a pathway that we use at home, or we use in the commercial industry to develop flavors. The idea, of course, lipid degradation, and you might say lipid degradation? I'm thinking of French frying. That's a degradation of the lipids due to high temperatures. Almost everybody loves that flavor. Who turns down French fries or donuts or these things? And then, of course, the last one is fermentation. And I wish I remembered the number as to what percentage of the food eaten is fermented. It's a really impressive number if we look at it on a global basis. It's a means of preservation, right? And so that's developed or crept into many cultures as a means to preserve foods. And now maybe preservation is less of an issue, but it's a cultural habit. So we're going to talk about all of these. George, have you talked about non-enzymatic browning? Not yet. Oh, that's good. So when George talks about it, keep in mind it's totally irrelevant to flavor. How about that? If I finish that sentence, I don't get in too much trouble, George. Because what George is going to talk about, he's going to talk about browning, and the data largely comes from nutritional studies, color studies, maybe even a little bit of off-flavor studies. But flavor is really different, and non-enzymatic browning is very different when we come to developing flavor than the things that we normally see in our textbooks about non-enzymatic browning. And a good example, or a good way to illustrate that is, if you take a food, you mix, well, let me think how I want to word this. I guess if you'd put a bunch of amino acids and sugars, that's what browning is, a reaction between reducing sugars and proteins or amino acids. If you take them and you heat them, they're not going to necessarily turn into chicken, they're not going to turn into beef, they're not going to turn into chocolate or coffee. Many of the food products that we do bake, we fry, we develop flavor during a heating process. Their nutritional value will go down, you'll get nice plots out of the whole thing, but you don't develop flavor in the same way. Flavor, I've got to go ahead and take all of these chemicals, the reactants in a food. I got to have the right materials, I got to have the right times, the right temperature, the right water activity, the right pH, and I will get beef. But that's not true in terms of the general reaction of the non-enzymatic browning. So when George talks about it, think about what I'm going to talk about and basically what you are. Because most people don't get the flavor part of it. They get the nutrition, the health aspects of it, and not flavor. So let's go ahead and take a look. It's a brief discussion of this topic. It's interesting that this flavor is what comes from the baking process. Now I know George loves bread, so that shouldn't be a problem. Baked bread, I salivate. You walk into a room where somebody says baked bread, it's automatic. A beautiful, beautiful fragrance that comes from baking of cereals. But then any fried foods, other foods, you bet, their flavor comes from this process. And it's interesting or funny to me that at one time, microwave was going to be the salvation of the food industry. Microwave was going to be the way that everything was cooked. Instead of spending 30 minutes in the oven or 2 hours in the oven, 3 hours in the oven, man, we're going to put this into a microwave, we're going to do it in 15 minutes, we'll have instant food. And companies invested a tremendous amount of money in microwave heating. It's so fast, right? Why can't we do that? And it was a kind of a blip like this. You know, it probably lasted maybe 5 years, and it was growing, the microwave, and it failed. It absolutely failed to reproduce, or replace, I should say, the traditional cooking methods. And it is because of how the Maillard reaction, how the browning reaction works. It isn't the same chemical reaction. If we look at microwave cooking, there's no surface drying. And so you put a loaf of bread. That was my task yesterday, a wonderful loaf of honey whole wheat bread. You put it in the oven, and the crust forms. The crust is kind of dry. It's the heat is drying out the surface. And we get the right environment for browning to take place. A little bit on the dry side, high temperature on the surface. If you've ever looked at a microwave, you can put a muffin in there, a loaf of bread in there, that surface does not get brown. It just doesn't happen. The surface doesn't dry. The temperature doesn't get to be the same. So one of the failures of the microwave was no surface drying. The surface temperature is actually below boiling. It's where water is evaporating. We're getting evaporative cooling off that surface. So it hovers at or just below the boiling point. The idea, no, some of the finest things come from simmering 3 hours in a nice saute pan or an oven. And you're not going to get that. Time, temperature, chemical reactions. And so 15 minutes doesn't replace the longer cooking times. It's interesting, too, of course, that we do lose water. Water's evaporating from that product, as the microwave works with it. And what does it do? It distills out the flavor. The flavor goes out with that boiling water. And so that was absolute disaster. So about 5 years, microwave was the king. 5 years later, nobody wanted to admit they ever had a microwave research group. It was just such a flop. Well, let's go ahead and go on. And now I did get ahead of myself in the sense that flavor, non-anesthetic browning, and as I said, most of the stuff you get in textbooks really deals just with browning from a nutrition standpoint. And so these are really some of the important variables: pH of the system, the acidity of your food system during heating, what amino acids are present, what sugars are present. Maillard browning is a combination of amino acid and reducing sugars like glucose or fructose, maltose, lactose, and so on. And water activity is also an important factor in influencing this chemical reaction. It's interesting to me that Maillard browning, this reaction has been studied for well over 100 years, and we still aren't in a good position to understand it or control it. And so there's still a good deal of work that needs to be done. When we do this at home and we try to produce things at home, yes, we do them in the skillet, we do them in the oven, we use natural ingredients, basically food ingredients, and we make this reaction go the way we want to develop the flavor we want. But the industry makes vegetarian chicken flavor. They make vegetarian beef flavor. Chickens never come close to that chicken flavor. When you buy the bouillon cubes or you buy chicken stock, there's a poor chance that the chickens ever come around. Maybe they got one outside the factory or something to show they have chicken. We don't do it, or the industry doesn't do it that way. What the industry has done is they studied, let's say beef, what the heck. They studied beef, they took raw meat and then cooked it, and they analyzed that. What was destroyed? What happened? What happened to the chemistry of meat as it went from fresh, raw to a flavorful product? And kind of the assumption is those things that were consumed, those sugars, those amino acids, those vitamins, whatever, that were consumed must have led to flavor. So they put a lot of time into studying changes that occurred during the cooking of meats, for that matter, cocoa, chocolate, any thermally processed food, and started to link back together. Oh, these are the components when heated under these conditions tend to give us a beef flavor or chicken flavor and so on. And this is kind of the outcome of work that started about the early 1960s. So it's been, 56 years that they've been studying the chemistry of these reactions and get been fairly good at putting together the right chemical reactants into a pot and heat those components instead of a piece of meat. And so for amino acids, there are a few amino acids that have been shown to be absolutely critical. 2 flavor precursors. Sulfur. What do we have? Cysteine, cysteine, methionine. 3 amino acids. They're absolutely essential to making something taste like meat. And so I'm going to take these things, I'm going to put them in my kettle, right, my pot, and I'm going to heat it. So what do I throw in? I throw in cysteine, cysteine, and methionine. Methionine will push it more like potato, so a little bit of stew-like character. Cysteine, cysteine give it more of a beef-like character. Valine, alanine, they're really nice in cocoa. So I would dump these, and if I'm going to make a cocoa flavor, I would use valine and alanine. So there's one of my reactants. I need, for Maillard reaction, I need a reducing sugar. The amino acid primarily determines the flavor. The sugar kind of makes it happen, that's all. So sugars facilitate, but the amino acids control the flavor. So I can do just any 2 reducing sugars. Xylose and arabinose are nice sugars. I'm sorry, xylose and glucose are nice sugars. So in my pot, I'll put my amino acids, I'll put my sugars in. To get them to react, I have to put a little water in there, so we got a solvent, a chemical reaction system. pH. If you look at meat, the pH of meat is something like 5.3, 5.4, in that ballpark. And so I want to have this reaction go towards meat flavor. So I start setting up an environment. Here are my chemical reactants. Let me set up the environment so these reactants go the right way. And so in this case, we'll look at meat. So if I want a meat flavor, I will adjust the pH of this water amino acid sugar system to about pH 5.3. Okay, that's what meat is. The reaction went the right direction, good. Then I'm going to have to go ahead and heat this system. And so how much do we heat it? Well, again, you look at the cooking of meats. If I'm going to make a stew, if I'm going to make a soup, lots of water and fairly low temperature. It's just boiling temperature, right? And so I use a fairly low temperature, and that gives me more of a stewed flavor. It drives this chemical reaction to those components. If I want to have a nice roasted meat character, I'm going to have to increase the temperature, just like when you put it in the oven or on a skillet. So we're getting high temperature of that meat. So I'm treating my model system exactly, pushing it exactly the same direction as you do in the cooking process. So again, we need a skillet, we need an oven to get some dry surface, or we can put it into a pressure cooker, that type of thing. So let's even higher temperatures. We do have to look at water. Water influences chemical reactions. If you've all taken organic chemistry, you'd appreciate the fact how important water activity is in controlling chemical reactions. Meat, water activity is almost 1. It's almost perfect, the same as water. And so, again, your system has a very, very high water activity if I want it to go to meat. If I want to push it to chocolate, we roast cocoa beans, right? They're dry. So dryness eliminates many chemical reactions. There's no water to catalyze these chemical reactions. And so we develop chocolate flavor. This tends to give us, if we still stay with meat, this gives us a basic meat character. It's a savory character. If you want, I want a lamb flavor, a mutton flavor, I would take a little bit of mutton tallow and I would put that into my pot before I start heating it. And then that fat's going to break down to give me a mutton flavor or a lamb flavor. If I want a chicken, I'll use a little bit of chicken fat, and then chicken fat will break down to give me the flavor that I want. So it's really an interesting process. And so if you ever come across a beef-flavored vegetarian dish, don't worry. There probably was no beef that ever came near that. You don't need it. What you do is you mimic what nature did. You set up the right reactants. You set up the right conditions. And you will develop the same type of flavor. It's a tough one. It didn't come easily because if you look at meat flavors, any of your roasted, toasted products, they're extremely complex. We've identified over 900 chemicals, aroma chemicals in meats that have a significant contribution to flavor. So I got to get the right blend of those 900 chemicals or it doesn't taste like what I want. So you have to be pretty careful in how you put this all together and how you make it happen to end up getting the desirable flavor. And that little bit of bouillon cube or beef stock or whatever it is. And so that's kind of the Maillard reaction and how it works into, let's say, the industry and the things that you eat, for that matter, that develop on these flavors. Fats are also important to us. You'll probably be thinking about fat and fat degradation as being evil or being bad, undesirable. And that is true. If we look at the kinetics of how fat deterioration occurs, oxidation, at room temperature, it's not good. The kinetics, the chemical reactivity, push that reaction to things that are kind of unpleasant. But if we take those fats and we put them in a high temperature in the right environment, we get some nice stuff out of it. So the same fat at storage conditions can be off flavors. That same fat heated in a certain way under certain conditions is very, very desirable, very pleasant. And so we kind of keep a look at these things and say, okay, lipid oxidation, in our case, it tends to be good. It gives us this French fry flavor, donuts. I mean, think of all the things. Kentucky Fried Chicken, take your pick. They're loved flavors. It comes right down to it. Get a little bit of fat, a little bit of flavor. What could go wrong with it, right? Back a few years ago, fat was evil. And if you're around long enough, you start getting a kick out of the trends in the food industry. Something's good, it's good for a while, then it's bad. Then something else becomes good, and then becomes bad. And so at the height of fat being evil, I had the opportunity to speak to newspaper reporters in Washington, D.C., and I started off my presentation with I love fat. I absolutely love fat, and that was so counter to everything that everybody was saying. I got a kick out of it. And why did I do it? Because some of our most beautiful flavors come from fat. I like fat. I don't like it necessarily for calories. I don't necessarily like it for weight and all these other things. But you don't get flavor without it. You want to eliminate fat, you're eliminating flavor. No two ways around it. But the funny thing was, of course, getting the reaction and then trying to recover. But it was also then coming back to the department and being approached by every nutrition faculty member saying, Gary, did you really say that? You love fat? Yes, I did, actually. Anyway, okay, French fry flavor. We also get a special flavor from dairy fat, butter fat. One of the experiments that you should do at home, you absolutely should do at home, is buy some margarine, buy some butter. And take the margarine, put it into a fry pan and warm it up. And then smell it and look at it. If you want, go ahead and let it cool a bit and taste it. Do the same thing with butter. When you put butter into the fry pan and heat it, it develops a sweet caramel-like flavor. It's absolutely beautiful flavor. If you know what you get when you heat margarine under the same conditions? No one's ever done this with a skillet? You get hot margarine. It's really not very interesting. And what's the difference? Why does putting butter in cookies, why does putting butter in pie crust, why does putting butter in a recipe develop better flavor? And it really, really does. For one reason or another, The dairy fat, and isn't an inborn error in metabolism? I don't think anybody's ever explained this. But the cows put in some unusual substituted fatty acids. They've got some fairly middle chain length fats that are hydroxy acids. For some reason, the cow puts a hydroxyl group fairly close to the acid. And what happens is that destabilizes that fat. Those fatty acids break off during heating, and they go into a cycle to make a lactone, a very sweet caramelic note that comes from the unique fat of butter. Sometimes people say they use margarine in baking because it doesn't make any difference. It does make a difference, and this is primarily the reason. We also use fat, as I'd mentioned just on the last slide, to push flavors in certain directions, to make that kind of mixture of amino acids taste like chicken, taste like lamb, taste like whatever. A little bit of fat. That's, again, where some unique precursors come from. It's interesting, if you, at the end of this class, you kind of look at all of the chemicals you've learned about. I call them chemicals. We can call them ingredients, call them whatever you want. Fats are the only component in our foods that are fairly long molecules. Lots of carbon, 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 carbon. You don't get that with amino acids. You don't get that with sugars. You get those structures only from fat. And when you're cooking, when you're developing flavor, when you're favoring chemical reactions to develop flavor, some of those longer chains give you unique notes that you can't get any other way except for from fat. So fat is important to us. I worked with the major chip manufacturer a few years back, a potato chip manufacturer. They were brainstorming how they can develop better low-fat or no-fat chips, potato chips. And of course, their goal was no fat. And I sit and say, well, look, you can't do no fat. You can't create the flavor compounds without fat. We need this structure. We need these parts of these fats to be incorporated in flavor. And they, of course, went into, let's cook it longer, let's soak it longer, let's do this to it, let's do that to it. You're not going to do it without the right precursors, and that's fat. My argument is you don't need 30% fat in a product to develop flavor, but you do need some flavor, some fat in there to develop a characteristic flavor. Well, fermentation is certainly a big area as well, and we're not going to do this justice at all. Like I said, there's so many products that are fermented. And when you look at flavor development, the majority of flavor tends to come from primary fermentation products. Microorganisms are really good at producing acids and alcohols, aldehydes. We think of cheeses, yogurt, beer. These are the compounds that really tend to give us a lot of the flavor. And so this primary fermentation process, a wonderful source of flavor, wonderful source of preservation. Take your pick of fermented products. We have to keep in mind, though, that it isn't just the metabolism of the microorganisms. So the microorganisms take these sugars and they turn them into these metabolic products. And we eat those metabolic products, but it's more than just the metabolism. Because these microorganisms are wonderful enzyme factories, so they produce all kinds of enzymes. The microorganism may die, may have come to mature, die, but their enzymes will tend to live on. So we get metabolic activity, and then we get an activity of any enzymes that the microorganisms produce and leave in the product. So it's like I say, quite a factory going on. Well, that didn't do that justice at all, but you get an idea of how's that. So we're going to spend a little bit of time talking about off flavors in foods. What do you think is the number one criticism that companies get? If they get people calling in about their product and they're unhappy with the product, what do you think they complain about most? Vitamin C being too low? Maybe it's low in calcium? What do you think the most common criticism is of a product? You should anticipate its flavor, shouldn't you? Or I wouldn't be bringing it up. It is flavor. I think number two is actually you can't get the darn box open. They can't get the container open. But when it comes right down to it, flavor is a driver of consumption, of liking, purchase. There's absolutely no question about it. You can make something that's so good for you. People will eat it once, they'll eat it twice. The vast majority won't continue eating something they don't like. It's just a few people who will hold their nose and eat. We get a great deal of pleasure out of eating. You think about all the times and the way we use food in our culture. Like I say, flavor is exceptionally important to us. And so when it doesn't deliver, when we get off flavors, unpleasant flavors, it's a problem. And people will call in, people will complain. So I don't say that flavor is more important than nutrition, believe me. No, nutrition is more important to us. But flavor is also important. It dictates a lot of our nutrition. If we could make broccoli taste like ice cream, I don't think we'd have a problem in the world of nutritional deficiencies. So here's our problem. So let's kind of look at where off flavors come from. We'll get this introduced, but we won't get too far into it. We'll pick it up next time. So one of the major problems is chemical changes in the food. And by the way, we call that off flavor. There's been some undesirable chemical change in that food, like lipid oxidation, or like Browning reaction, Maillard-Browning reaction. Maillard-Browning is good in some cases, bad. Lipid oxidation, good in some cases, bad. So it can be good or bad. So this is off flavor, chemical deterioration. Microbial growth, that's not a change that's happening in the food. It's being acted upon by outside sources. So some microbial growth has added a taint to the food. There's a difference between tainting and off flavor. Taint is external. Some kind of contamination, so environmental contamination has snuck into our food supply. So this is what we're going to deal with, is these sources of objectionable flavor. How's that? I'll use the word objectionable. So off flavors and taints. So these are our major sources of chemical change. I put lipid oxidation at the top because it is the most common off flavor, most common source of off flavors in foods. So we're going to go through each of these. Non-enzymatic browning is kind of right there too. It comes up fairly quickly after that. Enzymes, residual enzymes, can give us, again, off flavors. And light catalyzed reactions. Light is energy. Light promotes chemical reactions, and it promotes things that aren't desirable for the most part. So let's kind of take a look at each of these. Lipid oxidation, it is the potential in most foods. When we talk about off flavors developing, we're talking about parts per million of compounds being formed. It isn't like there's 1%, 5% things that come and give it off flavor. It can be 1 part in a million, and that food is bad. It tastes bad. We have tremendous sensitivity to aroma compounds, to flavor compounds. So a little bit of fat deterioration goes a long ways in making that food undesirable very, very quickly. When someone comes to me with a food and says, Gary, this doesn't taste good, the first thing you do is, bring me a sample. Let's taste it and see what it is. So you taste it, okay, I pick up something too. Then we start looking at the ingredient statement, start looking at the product. To oxidize, we need unsaturated fatty acids. Stearic acid, palmitic acid are saturated fats. They don't deteriorate. They don't oxidize very quickly at all. But we get some oleic, linoleic, linolenic, arachidonic, all of these multiple double bonds. We've got time bombs just waiting for something to happen to them, and it will. It absolutely will. Our polyunsaturated, they're good for us, they're healthy for us, and yet we find they're a curse from a shelf life, from a product standpoint. So that's the first thing you look for. Are there unsaturated? What type of oil, what type of lipid was used in that food product? You also look at water activity. There's, again, what George will tell you about water activity and oxidation is absolutely right. There's a place where lipid oxidation is just very fast, the intermediate moisture foods. You kind of look at, is this dry, is it intermediate moisture? And so water activity is important. You look for things on the label, antioxidants. Did somebody put butylated hydroxytoluene? Did they add tocopherols? Have they added natural rosemary extract? These are all antioxidants that could be used. So you look at the label too. Okay, we've maybe got some fats that might oxidize. Have we put anything to stop that oxidation? So what antioxidants are present? Obviously temperature. Higher the temperature, the faster things deteriorate. And you also look for metals or enzymes, catalysts for this particular reaction to occur. And it doesn't take much, a few parts per million of copper, a few parts per million of iron, and it's a disaster. So again, you look for these factors when you start saying, if I'm in food product development, I want to know what's going to happen to my food. You really go through this list and look, have I set up a problem? Are there trace metals? What temperature will it be stored at? Water, what's the water activity, and so on. So again, a number of factors. Have you done lipids, George? Okay, so yes, you've done lipids. I've got about two more minutes, so we'll take at least one of those. How's that? But the first thing always is to taste the food. You want to know what's happened to it, you taste it. In the earliest stages of oxidation, it's stale. Stale's not helpful. Stale means the flavor just isn't what it should be. It's not fresh. So everything kind of starts off that way. But when it goes a little further, it tastes more like you'd expect cardboard, a wet cardboard, to taste or smell like. From there it moves on to metallic, really, really metallic flavor. And finally fishy. If it gets into the metallic and fishy state, it's an absolute disaster. It's gross. I can't think of a scientific word for that. So again, you always start off by tasting things. So let's call it quits here and pick up the off flavors and taints next time as well.
Thank you very much.
Sure.
Okay, see you on Wednesday.
Good. Hey, what slide are we on, George?
On the century.
40 what?
Yeah, 49.
49, okay.
Yeah, so
15, we got 70.
It's okay. I mean, if you don't finish on Wednesday, you can pick some.
Oh, no, I'll finish. I might be done earlier.
All right.
So let's see how that goes.
Okay.
I tried to say a little more background, a little